All right, so I'm going to work this problem from the homework. This problem's all over the internet. I guess a lot of people struggle with this just kind of out and about. And this is really a wonderful, wonderful problem. It's a little bit involved in that it maybe has 2 steps too many, but we'll go with it anyway. Okay, so Gayle runs, excuse me. Okay, Gayle runs at a top speed of 4.65. Let's just start highlighting the things that we're probably going to need. So this is going to be an initial velocity. She runs at a speed of 4.65 meters per second. It dives on a sled, initially at rest, on the top of a frictionless. Ooh, that's good. So we want these 2 things, right? Initially at rest, so that's the sled. A frictionless snow-covered hill, okay? When you see frictionless, you immediately want to start thinking about isolated. So it's isolated for collisions, but it also means that there's no non-conserved work, okay? So from this word frictionless, a lot of times, okay, usually it doesn't always mean that there's no non-conserved work, okay? It means non-conserved work is 0, but certainly there's no work being done by the surface of the snow. But it also means that it's isolated, so if there's a collision, we may just, conserve momentum, okay? After she has descended a vertical distance of 5 meters, her brother, oh my God, there's another guy, who was initially at rest. I wish they gave her brother a name. Is initially at rest, so he's initially at rest, hops on her back, and together they continue down the hill. Okay, still frictionless, still no conserved, non-conserved, and it's isolated. What is the speed at the bottom of the hill? The total vertical drop is 16 meters. Okay, so one thing to note, this is the initial drop, and then this means that the final drop is actually 11 meters, right? Because, we're going to go 5 at first, and then we're going to go another 11 that second step. Okay, and then they're going to give us some information. So Gayle's mass is 50. The sled has a mass of 5 kilograms, and her brother has a mass of 30 kilograms. Okay, so her brother is smaller than she is. So it's a little brother. Okay, so let's start by drawing a picture. And let's see what we've got here. Okay, so Gayle's running. Here's a little, Gayle. And she's running this way at 4.65 meters per second. And then she's going to jump on a sled. I don't know what sleds look like, so let's just draw the sled like that. So she's going to jump on there. I guess she's not really going to, drop into it like that, right? But she's going to basically become a part of the sled, right? So all of a sudden, she's going to be here on the sled. And then she's going to ride the sled down a vertical distance of 5 meters. I don't know what we want to call that. Let's call that H1 equals 5 meters. 5.00 meters per second. Oh, no, just meters, excuse me. All right, let's see here, 5 meters. Okay, I guess we should call this V0, right? That's V0, is 4.65. Okay, so now she's gonna drop 5 meters. Let's see here. Note that as she rides down it. So then, all right, so 5 meters down the hill, her brother, who I'm going to do in blue, he's just going to be chilling, waiting for her, right? So 5 meters down the hill, she's going to run into him, right? Or not run into him, hopefully. She will run in and be next to him, right? So when she gets here, she's going to be cruising like this. And now her brother's going to jump on board with her, right? So her brother's going to be here with her, okay? So now she's going to drop a further 11 meters. Okay, so now we're going to go down another 11 meters. Okay, so there's another 11.0 meters. My vertical abilities are getting quite poor here, right? So anyway, let's try to draw that closer to the real thing. And that further 11 meters will take them down some spot down here. It does say at the bottom of the hill, so maybe I'll round out my hill. So there's the bottom of the hill, and there's the 2 of them. They're happily doing their thing. Now, of course, It shows that I'm a Southerner. I know nothing about sledding because I have them riding it standing up because these people are awesome. Okay, so there you go. So we know that the mass of the brother is 30 kilograms. Sorry, I was already on blue, so I just kind of kept writing. So let's just kind of like store all my information over here. 30 kilograms. I know that the mass of Gayle is, 50 kilograms? 50 kilograms. And the mass of the sled is much smaller, 5 kilograms, 5.00 kilograms. So it looks like we're going to have 3 sig figs here, right? Okay, so let's zoom in and, what we want to know. So now what we want to know is what is their speed at the bottom of the hill? Okay, so I want to know the velocity here equals what? Okay, so I'm going to start labeling basically times in this, in the problem, right? So this problem has a lot of different things going on, and that's what makes it kind of annoying, right? So I call this V0 because this is the beginning of the problem. Okay, she's going to run along and she's going to jump on the sled. Then the sled has no velocity. So I'm going to call this point in so this will be times 0 is before she jumps on the sled. I'm going to give you time 1, which is after she jumps on the sled, because the sled has no forward momentum, so it's going to slow her down, right? She's basically colliding with the sled. The sled is going to take some of her momentum, and it's going to speed up, and she's going to slow down. Okay, now, she's going to ride that sled this distance down the hill, okay? And so there's going to be her. Let me get rid of Greg, who's waiting there. We don't care about him waiting there. I mean, I guess we kind of do, but here she is the moment before Greg jumps on. Or, sorry, I keep thinking of him as Greg, Gayle. I keep thinking of the brother as Greg. I don't know why. But right before the brother jumps on, she has some speed. She is sped up from 1 to 2. All right? And there will be could you solve that? You couldn't solve that with kinematics, I don't think. No, you would not be able to do that with kinematics. You'd have to know some angles and things like that, which they don't give us. So basically her potential energy, we have to do this with energy. Her potential energy from 1 to 2 is changing into kinetic energy. Okay, at 2, her brother jumps on, and now we are at point 3, okay? This is another collision, right? So she and the sled have a certain amount of momentum, and her brother doesn't have any momentum. So as soon as they collide with the brother, they're basically going to become one mass. And at that point, so it's an perfectly inelastic collision, right? So the brother jumps on, there's a collision right there. Okay, so after this particular collision, they're going to slide the rest of the way down down the hill. Now again, this is just an energy problem. Their potential energy is turning into kinetic energy. So when they get to the bottom, that will be 0.4. Okay, so here's what I'm going to do. Where there are collisions, okay, let's remember that. There's a collision between 0 and 1, right? There's a collision between 0 and 1. So I'm going to draw a big star, like that's the collision. Okay, there's another collision between 2 and 3. Okay, both places where there are collisions, okay, and in each case, there's a collision that is isolated. Yes, it is isolated because there's no outside forces because it's frictionless. But the other thing to note is that there's a collision between something stationary. So so between 0 and 1, there's a collision between, is that how they do between? I think so, maybe, let's just write between Gayle and a stationary sled. Stationary sled, right? So we will use momentum here. So we will use a momentum equation here. And it's great because it's isolated, so we can do that, right? As I've mentioned to you guys, in high school physics classes, they almost never have non-isolated collisions. I really don't know why. I don't think it's that hard. But okay, so up here we've got this second star. Okay, now we've got a collision. This is our other collision. And this collision is between, Gayle slash sled and stationary brother. Stationary bro, right? And so again, we'll use momentum equation here, right? It is an isolated system because there's no friction. We've removed the friction from the problem. So between 2 and 3 and between 0 and 1, we have to do the momentum equation both of those times. Okay, now between 1 and 2, maybe I'll use like blue or something. Okay, between 1 and 2, all we're doing is going downhill. Okay, so this is potential energy converting into kinetic energy. Okay, so we will use the conservation of energy. Okay, conservation of energy. Okay, now note we've got this same thing going on down here, which from 3 to 4, we've got potential energy becoming kinetic energy. So that's just going to be conservation of energy, or really conservation of mechanical energy, right? And that, of course, works because I'll go ahead and call it, well, mechanical energy. Mechanical energy. Okay? So that's our whole step. So basically from 0 to 1, we're going to do a momentum equation. From 1 to 2, we'll do conservation of mechanical energy. From 2 to 3, we'll do a collision between the Gayle and the sled, so we'll do another momentum equation. And then from 3 to 4, we will do a conservation of mechanical energy. So that is the process here, okay? And I'll try to come back up to this diagram as we work in order to label the answers that we get. Okay, so from 0 to 1, we've got a collision between Gayle and a stationary sled. So let's go over here, and let's just, I guess we can zoom way in and do that, right? Let's do it, let's zoom in pretty good, okay? So here's our collision. Let me see if we can just isolate that portion of it, right? Okay, so we got a collision, and it's a perfectly inelastic collision. So here's our conservation of momentum equation. Conservation of mom. We need enough moms in this world, right? Okay. So mass of Gayle times the velocity of Gayle. Call that V naught. Vg naught. Velocity of Gayle naught. Okay, plus the mass of the sled times the velocity of the sled naught. Now we know that before this particular collision, the sled is not moving, so we're not really worried about that. Equals, now they become one object afterwards, so I can say mass of Gayle plus mass of the sled times the velocity, what do we want to call that, right? Well, we know it's going to be 1, right? Let's call that velocity of Gayle and sled 1. Excuse me. Okay, so let's solve for VGS1. So VGS1 then equals, let's see, we're going to rearrange, mg Vg naught over mg plus ms. Okay. So let's go ahead and plug and chug and solve that sucker. I will pause as I do this. So let's keep that collision in play. Okay, so there we go. We've got, if I plug the numbers in, she's going to slow down ever so slightly, right? So she was going 4.65 meters per second, and then she collided with something that wasn't moving. So it slowed her down. She sped it up, okay? And so all told, the sled is sped up a lot, right? It went from 0 to 4.2273 meters per second. Well, she slowed down a little bit because she went from 4.65 down to 4.2273. Okay, remember, for this particular problem, I think we're going to end up at 3 sig figs. And so I'm just keeping in a lot extra right here. Okay, technically this particular answer has, well, this has 3 sig figs, this has 3 sig figs. I mean, the original numbers, right? This has 1 decimal place. This has 2 decimal places. So 55 becomes 55.0. So this has 3 sig figs on the bottom. So we're going to want 3 sig figs in this particular answer, right? I'm going to keep 5 just so there's no rounding errors. But let's just keep track and remember that we got 3 sig figs here. Okay. So I'm going to go up to my drawing. And here's, so now she is beginning down this hill. And she is going at Gayle and the sled at point 1 are going 4.2273 meters per second. Okay, now she is going from 1 to 2. Okay, so 1 to 2, we're going to do a potential energy, kinetic energy, conservation of mechanical energy. Okay, I don't know that I have enough room in here for a conservation of mechanical energy. So let's just go up here and we'll do the math over here, okay? Okay, so this will be from, so conservation of E, mechanical energy, okay? Now remember E is defined as all the kinetic energies plus the potential energies, right? Okay, I could just say the summation of all of that, really. Okay, so so this is going to be from 1 to 2, okay? So from 1 to 2, all we're really doing is we're just dropping by 5 meters, okay? So here's the equation for that. Conservation of mechanical energy is work non-conserved equals the change in energy, really, right? So I'll write it like that for now, okay? And so, and I've always done it before as change in KE plus the change in PE, right? Okay, so then we'll note that there's no non-conserved forces here on this particular problem. That's why it was frictionless. So 0 equals, what's the change in kinetic energy? Well, let's see here. Okay, so 0, the change in energy is 0. Okay, and basically we have kinetic energy that's changing into potential energy. So the initial kinetic energy is 1/2 the final kinetic energy, mv, what are we calling that? V Gale and sled at position 2. So this right here is position 2, and that's Gale and the sled. Okay, so we'll call that V Gale and sled 2 squared minus 1/2. So this is the initial kinetic energy. I call that GS, MGS, Gale and sled. V squared, Gale and sled 1. Okay, cool. There's our change in kinetic energy. Now what about our change in potential energy? So remember we always do mg delta H, right? So plus mg, and we need the delta H. Okay, now remember this is G is GS, and the delta H here is going to be, they went down 5.00 meters. Okay, I'm not plugging that in just yet, but we'll get there, right? So what we want to solve for here is we want this particular quantity right here. Okay, we don't want it squared, but we want it, right? So let's go ahead and rearrange this so that we can get that the way we like it. Okay, so I'm going to take this and bring it over to the other side. I'll take that and bring it over to the other side. And then once they're over to the other side, I'm going to divide by 1/2 MGS. In fact, right now, before I even do that, I'm going to get rid of MGS because it's in every single term, right? Okay, so we're going to leave this alone, and we're going to bring everything else over to the other side. So this term is going to be 1/2 VG Gale in the sled 2, so that's after it has fallen some distance, squared, equals. Now I'm going to bring this over to the other side, so the sign will change. So it'll be 1/2 VGS1 squared. Okay, and we're going to bring this over to the other side. So its sign is going to change, switch G delta H. Okay, cool. Okay, now I am going to want to get rid of those 1/2s. So I'm going to put a little 2 right here. And now I'm going to get rid of this guy right here, this little 1/2, and I'm going to get rid of that little 1/2. Okay, the next thing I want to get rid of is I want to get rid of that squared. So I'm going to take the square root of this side. I'm going to take the square root of this particular side, which means that little 1/2 is going to go away. Okay, and that's my expression for velocity of Gale and the sled at position 2 as a function of their speed at position 1, which was at the top of the hill. Okay, so I will now plug and chug. You may, I'm just going to pause and do it. I want to note, just to be very, very careful, that my delta H is a negative value. Okay, and if you don't plug in a negative value right here, what's going to happen is it's going to look like the sled slows down, right? Because we've got this negative here, and it's going to cancel with that negative right in there, right? So it's going to cause things to quote unquote speed up, or no quotes, it will speed up, right? And it's because we're going downhill. Okay, so let's, I'm going to plug and chug. Okay, so what I'm getting is 10.769 meters per second. Okay, Now, I want to note that this is an interesting sig figs issue. So in blue, I kind of, I was kind of thinking about, the sig figs here, right? So this particular, squaring that first term gives me 17.9 because it's going to have, the original number had 3 sig figs. Okay, and then this, once I square it, I end up with 3 sig figs. This right-hand term, all of those have 3 sig figs, so I end up with 3 sig figs. When I add them, right, I've got 1 decimal place in both of those, so I need 1 decimal place in my addition. So now I've got 4 sig figs. So we are in a really strange place where the number of sig figs has actually increased. So technically this number right here, this 10.769, needs 4 sig figs. And as you guys know, I like to make sure that I don't have any rounding errors. So what I'm going to do here is I'm actually going to add an extra sig figs to make this so that I don't have any rounding errors at the end, because 8, 9. So now I've got, 6 sig figs in my, working answer, so that I don't make a sig figs rounding error at the end, right? Because I know that this particular number has 4 sig figs. That is an annoying number of sig figs. Okay, luckily, the book doesn't really care, and this problem is inordinately complicated or inordinately, involved, right? Because we just have to keep doing stuff. So 10.7689. All right, 10.7689. So now we're down here. So at 2, velocity of the sled and Gayle and the sled, I think we've been doing GS at position 2 is 10.7689. 7689 meters per second. Now we're going to collide, right? We're going to collide with the little brother. So from 2 to 3, I need to do a collision between Gayle and the sled, okay, and the stationary brother, right? So this is what we're going to do right now. Okay, so let's do that over here somewhere. Okay, collision between Gayle and the sled and the stationary brother. Now remember, after we get the stationary brother on there, we're going to, the stationary brother is basically, becoming a part of the sled. So this will be another perfectly inelastic collision. Okay, so perfectly inelastic collision. So this will be conservation of mom, right? Conservation of momentum. Okay, so beforehand, we've got momentum of the Gayle and the sled. So mass of Gayle and sled times the velocity of Gayle and sled before that collision. I believe we called that 2, right? So this is right here. And then afterwards, we've got this, right? So, okay, so the momentum beforehand is here. And then it's all going to go into a much larger object, right? Technically, I guess we could add the brother on here. We could say, well, plus the mass of the brother times the velocity of the brother at 2, right? But we know that the brother's not moving, so that whole term goes away. Okay, so the momentum of Gayle and the sled plus the momentum of the brother beforehand equals the momentum of Gayle, sled, and brother. Jeez. Let's just call that we'll just call that mass total times the velocity of the total after the collision, right? So that'll be at position 3. Okay. What we're looking for here is the total velocity of everything. Okay, so let's go ahead and solve for that. So the velocity of everything at position 3 after the collision equals mass of the Gayle and the sled times the velocity of Gayle and the sled at 2 divided by the total mass. Okay, I'm just going to, we'll make a note that the mass total is the mass of the sled plus the mass of Gayle plus the mass of the brother. Okay, so I'm just going to call it MT. I think you guys can follow that. Okay, so velocity of everything at position 3 is going to be mass of Gayle and, well, you know what, I'm going to pause while I plug in chug. Okay, and so I'm getting a number kind of like this. Not kind of like this, exactly like this. Sig figs are getting really obnoxious, right? So I'm keeping 6 at the moment. Let's see if that is the correct number to keep. right? This number has 4 sig figs. Okay, this number, remember that's 5.00 and 50.0. So it's 55.0, so this has 3 sig figs. Okay, so on the top, when I multiply those two, I've got 3 sig figs. Okay, now on the bottom, this has 2 decimal places, this has 1 decimal place. Remember that's 50.0, this is 5.00, and this is 30.0. So we're going to have 85.0, so that's 3 sig figs on the bottom. Okay, so when we divide 3 sig figs by 3 sig figs, we're going to end up with 3 sig figs, which means at this point, I can take this particular number, and I like to keep 2 extra, so we will keep 2 extra. And so I want to keep 5, so I don't have any rounding errors. So 6.9681 meters per second, and that will be enough. Okay, so the total velocity at point 3 is that number. Okay, obviously we have a little more precision than we need, but that's enough to make sure we don't have any rounding errors, right? So there you go, velocity of the total at 3. So let's go up to 3. Okay, so at position 3, well, I've been doing this in black. Let's stay in black here. Dadgummit, I said black, you jerk. Okay, here we go. Okay, V total at 3 is 6.9681 meters per second. Okay, notice that after the collision with something that had, was fairly sizable, the brother's 30 kilograms, and they were coming down at 55 kilograms. And the brother sped up from 0 to 6.9681 meters per second, and the Gayle and the sled slowed down from 10.7 down to, basically 7 meters per second. Okay, and that makes a lot of sense. Okay, so now everything is together, and we're gonna go the remaining distance from 3 to 4. And remember, this is a conservation of mechanical energy problem. Okay, which I will work. I guess we'll work it right down here. Okay, so conservation of mechanical energy. Okay, which looks like this. Let's see here. So we've got, work non-conserved equals the change in energy. Okay, the change in mechanical energy. Okay, and the change in mechanical energy is change in kinetic energy plus the change in potential energy. Okay, we are, note again, remember, is no friction. Okay, which means there's no change in energy, which basically means we got 0 equals. Now, what's the change in kinetic energy? Well, it's the final kinetic energy, 1/2 mass total times the velocity final, right? Which is what we're looking for, right? So down here, we're looking for this. Okay, that is the answer to the whole problem. So I will call that velocity at 4, velocity of everything at 4 squared plus 1/2 m total. Oh, not plus, we're subtracting, right? It's a differencing thing, right? The change in kinetic energy. So the final kinetic energy minus the initial velocity T3 squared. Okay, plus the change in potential energy, which again, mg delta h. Okay, again, remember from the beginning of this problem, we are going to drop this remaining 11 meters from 3 to 4. Okay, so remember that delta H is going to be a negative 11.0 meters. Okay, that's the only tricky number in all of this. Okay, now what's nice here is this is the exact same thing we just did. Oh, this is MT, is it not? Okay, so what we're going to do is I'm going to rearrange, right? And remember that what we're solving for here is VT4, so we want this guy right in here. So I'm going to rearrange for that guy. I'm going to take this term and that term and bring them over to the other side. Okay, so we're basically going to flip those signs, right? So I'm going to start with 1/2 MTVT4 squared equals, I'm going to flip the sign on that, 1/2 MTVT3 squared, flip the sign here, MTG delta H. Okay, I guess I could have done it a second ago, but I'm doing it now. We're going to get rid of all those MTs because it's in every single term. And I want to get rid of that 1/2, right? So what I'm going to do is I'm going to put a 2 right here, and I'm going to and multiply that by 2 and multiply that by 2. So those go away. Okay, so now I want to get rid of that square root, so I'll say VT4 equals the square root of VT3 squared minus 2G delta H. Okay, a big grammar error here, not grammar, algebra error here is people want this to cancel with that, but that is a big no-no. Okay, those two do not cancel, so just be very careful there. Okay, so let's go ahead and plug in chug. So VT4 equals the square root of VT, well, you know what, you don't need to watch me plug in chug. Okay, so we end up with something like this, which sounds kind of fun, right? She was running at 4.65 meters per second at the very beginning all by herself, and she ends up on the bottom of the hill with her brother moving much, much faster. Oh, but we have to worry about sig figs, don't we? Which is totally annoying. But anyway, let's consider. Okay, note if I consider what came out of the calculator here, this thing came from, this is an infinite. This number has infinite sig figs, but this had 3 sig figs. This had 3 sig figs, so this answer has 3 sig figs. So this is 216 technically. This particular number had 3 sig figs and was squared. So this number is technically 48.6, right? So I'm going to add these two together, right? We're going to get 1 decimal place, right? So that's going to give me a number like 264, right? Which then I'm going to take the square root of 264. But basically, we've got 3 sig figs here. So when I take the square root, I'm going to have 3 sig figs. So we're going to round this to the 3rd sig fig. Okay, so VT4 equals 16.3 meters per second. Okay, this is a lovely, lovely problem. The sig figs notwithstanding, which is totally obnoxious. But there you go, 16.3 meters per second. It got kind of nasty in there, or just ugly, right? I should work on my animations. So that's it. I hope that was helpful. And that was 32 minutes on one problem. Could be done a lot quicker without worrying about sig figs. So, among other things, right? So I hope that was helpful. All right, y'all take it easy, and hope all's well. Bye.